like you did that in high school.
No, it was not.
Really?
Yeah, definitely not.
I was, but I was only doing intellectual, and I was getting portraying intelligence. And then after a month, they were like one of them and their parents, and then.
When I started high school, I was 5'9".
I don't know anything that's not in the metric system.
I
That's
was like 50 kilos.
no, it's pretty small.
Yeah, I was 50 kilos for the first
Okay, so we start with Rachel talking about adaptive sampling.
Hi. First of all, I'd like to thank the organizers for inviting me to this wonderful workshop. It's really a pleasure to be here. So I'm going to talk about adaptive sampling in matrix completion. I'm very happy that Yushin gave such a nice talk on the optimization side of matrix completion right before lunch. It really is a good segue into what I'm going to talk about. So I want to start with, very quickly go through the sort of older classical results on matrix completion, which are now 10 years old or so. So the setup is that there's some matrix M, we don't know it, but we can see some entries of the matrix. And we want to exactly recover or complete the hidden entries from only a few entries that we see. A common assumption to make the problem well posed, and which models real types of matrices in the world, is that M has low rank. So if I'm going to assume for this talk that the matrix is squared, just so one fewer parameter, but everything here extends to rectangular matrices also. So an n by n matrix, which is rank R, means that it's degenerate. In some sense, it has a skinny singular value decomposition, and essentially only has on the order of 2 times n times r degrees of freedom, as opposed to n squared degrees of freedom. Because of this reduced number of degrees of freedom, we can imagine that we could complete such a matrix, given only the knowledge that it's rank R, from on the order of n times r revealed entries. And that's where the story starts. Of course, we know that the low rank assumption is not strong enough. There's the canonical, or something similar to the bad example where we have a rank 2 matrix, which just has 2 1s and 0s everywhere else. This is a rank 2 matrix, and we're never going to see the 2 non-zero entries of the matrix from a number of samples that's order n times r, let alone less than n squared over 2. Okay. So in the setting where we are oblivious to everything except that the matrix is low rank, that's not going to work. We have to add an additional structural assumption, and a common one is that the matrix is not only low rank, but incoherent. So incoherence and matrix completion has evolved a little bit from the beginning. And now the usual assumptions of incoherence are more simple than they were previously. What we mean by incoherent is if we look at the matrix M and its skinny SVD decomposition, that if we look at the left and right leverage scores, these are n left leverage scores and n right leverage scores. And the ith left leverage score is just the angle between the left singular subspace associated to M with the ith canonical direction. Okay, so it measures how aligned the matrix is on the left with the ith canonical basis vector. And same for the right singular vectors. Okay, so an additional structural assumption besides low rank is that the underlying matrix has uniformly flat leverage scores. And that's more or less what incoherence in matrix completion is. So uniformly flat leverage scores, according to this normalization, means that all of the leverage scores of the matrix are essentially on the order of R divided by N. That's the normalization, times a constant K. So this is a very special situation because, in fact, the maximum value of K can be N divided by R. The leverage scores can go up to 1, as in this bad example, where we have 2 leverage scores equal to 1 and the rest equal to 0. Okay, so this uniformly flat assumption is a very, very strong structural assumption. But on the other hand, it's not as strong as the original incoherence assumptions in matrix completion were. I just want to point out something that matrices of this type are incoherent. Just block diagonal matrices where the values, where the blocks are the same sizes, and the values of the entries of the matrix can be different on the different blocks. So that's a perfectly incoherent rank R, where R is the number of blocks matrix. So we don't have to have like a Gaussian random matrix or anything like that, but just a sense that all of the rows and all of the columns are equally important in some sense, are balanced. If the blocks in this matrix were vastly different sizes, then we would become more and more coherent. The leverage scores would become more unbalanced. Please ask me questions at any point.
So this is for a constant number of blocks, right?
This is for R blocks. So R is the rank. And so if you do the calculation, then you get that all of the leverage scores are R over N. So as small as they can be. Okay. So after many works, and probably more that I couldn't mention here, I think most recently with Yudong Chen in 2013, we have the following sort of uniform sampling matrix completion result given an n by n matrix M of rank R. If we reveal entries of the matrix in a very oblivious random fashion where each entry is observed independently with a probability P, go through the matrix to do that. And we consider, for example, the nuclear norm minimization problem, which is a semi-definite optimization problem, the relaxation of finding the matrix of minimal rank, agreeing with the measurements. This will exactly recover or complete the underlying matrix with high probability, provided that P, the probability that we sample any given entry, is greater than or equal to the maximum among all of the leverage scores of the matrix times the universal constant times log squared n. Okay, so remember that in the best case, this max Li Rj is on the order R over N. In the worst case, it's order 1. In particular, what this implies for the sample complexity is that the expected size or expected number of entries under this sampling model is on the order of P times n squared, which is the max leverage score times n squared times log squared n. Okay. So you see that in the worst case, when the leverage scores are very unbalanced, this gives us nothing. This says we have to sample the entire matrix. In the best case, when the leverage scores are flat, this says order R times n times log squared n entries is sufficient. And we know that that's optimal in terms of the degrees of freedom of the underlying class up to the log squared n term. So for the remainder of this talk, I'm going to regard log squared n as a constant, meaning I'm going to talk about results that use this result. And if the log squared n term can be removed in this result, then they can be removed in those results. Almost surely one of these log n factors is not necessary. But I don't think that that's been improved in this general setting. And again, I'm not advocating that we use nuclear norm minimization with CVX on your laptop. There are many faster alternative algorithms like non-convex algorithms operating on the factored matrix that should have the same or comparable performance. Any questions? Note one thing is that the condition number of the matrix M does not appear anywhere in the conditions. The condition number of the matrix is an independent structure from the leverage scores of the matrix. So the matrix can be as ill-conditioned as possible, as long as it's rank R. and that doesn't change this result. Okay, so we want to ask, there's this obvious, or not obvious, but there's clearly a relationship between the model of sampling entries of the matrix IID uniformly and requiring some structural assumption like uniformly flat leverage scores. So more generally, what relationship can we say between the leverage scores of a low-rank matrix and an optimal sampling strategy? And that led us to take a closer look at how the sampling strategy is connected to the leverage scores. So again, remember that the leverage scores are just the angles of the left and right subspaces of the matrix with each of the n coordinate directions, or just the norms of each of the n rows of U and V. So if an oracle told us bounds on these quantities, these numbers Li and Rj, gave us sort of this information about the matrix, then you can imagine we might want to sample entries from a weighted probability distribution where we're going to sample an entry ij with higher probability if it's more important, meaning that the sum of the row and the column leverage score associated with that entry is higher. Okay. So this is general idea behind important sampling and designing optimal sampling distributions for like Monte Carlo sampling and things like that. So maybe not necessarily Li plus Rj, maybe Li times Rj, but something like this. In particular, for the bad example on slide 2, this would say we're just going to sample that corner with the ones in the matrix more frequently. And these leverage scores, although only more recently introduced in the matrix completion problem, one-sided leverage scores have a long history in the column or row subset selection problem for matrix sketching, which is the older problem where you have a low-rank matrix and you can subsample columns or rows of the matrix, and you want a good subset of columns that gives you a good representation of the entire matrix. And there, a good way to sample columns is according to one-sided leverage scores of that matrix. Okay, so what we did is we generalized the matrix completion result. So we assume we have a low-rank matrix M, and an oracle has given us bounds on its leverage scores. So we know Li and Rj. And so we can derive a good way to sample that matrix. So if the ijth entry of the matrix is, we observe it independently with the probability Pij, which is greater than or equal to the sum of the ith of its corresponding row and column leverage scores times, again, log squared n and universal constant c. So if the ijth entries is sampled according to this, a probability greater than this, then we can recover or complete the underlying matrix from these samples, and an expectation, this number of samples is on the order of r times n times log squared n times constant c. So now we've removed any dependence on the coherence factor, and this is, as few measurements as we could hope to have to take to recover a low-rank matrix up to the log squared n. Okay. And of course, the uniformly flat leverage score, uniform sampling is a special case of this theorem. And the key idea is to refine the sort of dual certificate type proof for matrix completion, where we derive concentration results with respect to a weighted L2 infinity matrix norm instead of entry-wise L infinity norm. So just more refined concentration bounds on a norm that's tied more closely to the spectral norm of the matrix. So this is still several years old. So for several years, I guess it's been more than 3 years. I thought, well, this is nice, but this, of course, this theorem requires still a lot of knowledge that we know the leverage scores of the underlying matrix. So I guess in some settings, you could imagine that you could have some bounds on leverage scores. They could be learned as, say, priors from some class of training matrices that you're interested in. But typically, this is very strong, and we would like to assume that we don't have any information about the leverage scores a priori. So the natural question is, if we're still in the setting where we can just learn about the underlying matrix by revealing entries of the matrix, is it possible to learn the leverage scores of the matrix along the way while completing it in a way where the total sample complexity or the total number of samples we need results in a lower number than the number of samples we would need just from uniformly IID sampling of the matrix. And that seems possible given that we're asking for only 2n pieces of information, 2n leverage scores, versus 2 times n times r degrees of freedom, which is to complete the entire matrix. And it could seem even more plausible that this could be possible because if you look at the result, we only need to bound the highest leverage scores, the largest leverage scores of the matrix, because if we sample from a probability that's greater than the little leverage scores, that's fine. It doesn't matter. So the unimportant rows and columns, we don't need to know. So in fact, we just need estimates for the large leverage scores. So we would like to try to do this to see if we can adaptively sample so that we can learn the leverage scores and complete a matrix and beat the number of samples one would get from the uniform sampling bound. So our first try at a sort of adaptive or two-phase low-rank matrix completion algorithm is as follows. Just given a budget of m samples that we can take and a parameter between 0 and 1, first just draw m1 entries of the matrix via the uniform sampling model. Okay, because we're oblivious and we don't know anything except we're assuming the matrix is rank R. So then from the zero-filled sample matrix, find its best rank R approximation, because you can only take leverage scores of a low-rank matrix. The leverage scores of a full-rank matrix they're always 1, because you have orthonormal U, sigma, V are orthonormal. So take the rank R approximation to the sort of the zero-filled sample matrix, and then we have sort of estimates of the leverage scores of the underlying matrix. And then from these estimates, generate a second batch of measurements, a second batch of entries, M2, according to the weighted distribution given by these estimates. And then we've taken a number of samples, M in total, and throw all of these samples into, say, nuclear norm minimization and complete the matrix and see what happens. And so we found that gamma equals 0.75 seemed to be a good choice, corresponding to adding more samples allocated to the phase 1 uniform sampling. And I have this very sad little picture. It's really embarrassingly sad, but it's all I have, so I'm going to show it anyway. This was a typical simulation result. We looked at 400 by 400 rank 10 matrices that had a power law structure, so of the form D times U times V transpose times D, where U and V are tall, thin, IID Gaussian matrices. So that would create a roughly incoherent matrix, but then we reweighted the rows and columns by D, a diagonal matrix with power law entries. So when the power alpha in the diagonal matrix is 0, we just have an incoherent matrix, and when it's 1, we have a pretty coherent matrix. And then we did the two-phase matrix completion algorithm on the previous page, and we looked for the oversampling factor we need in order for matrix completion to work with high probability. And so as the coherence increases, we see that we do need more samples with the two-phase sampling, but the sample complexity is far, far better than what uniform sampling needs. So uniform sampling really, really becomes very bad when the matrix is coherent. And then, I don't know, but you see this black line, which is the sort of oracle distribution leverage score sampling, which is what we would need if we knew the leverage scores a priori. Okay, so this suggests that adaptive sampling and matrix completion can really help in reducing the complexity when the assumption of incoherence is violated. So we wanted to look into this, but unfortunately, we could not derive any theory for this. All of the results in the literature we found on how good estimates of leverage scores you can get of a matrix from its samples, none of those results were strong enough to prove that this could lead to smaller sample complexity than uniform sampling, just the same. But then we remembered, but for matrix completion, we don't need to estimate all the leverage scores, just the large ones. We just need to know the large ones. So we looked at a different algorithm that's simpler to understand, at least for me, but not really the algorithm that you want to use. So keep that in mind. So if we have our low rank matrix, our rank R matrix M, and it has, now I'm bringing the condition number into the talk, which I didn't want to, but alas, the condition number, the ratio of the largest over the smallest singular values of the matrix, then there's a relationship between the squared L2 norm of the ith row of the matrix and its ith leverage score. So the L2 norm of the ith row of the matrix is always going to be less than or equal to the ith leverage score times the largest singular value squared, and it's going to be greater than or equal to the ith leverage score times the smallest singular value squared. So in the ideal setting, when the matrix has condition number 1, then as long as you know the norm of the matrix, you get all of the leverage scores exactly from the row and column norms. So that's one. So we're going to use row and column norms of the sampled matrix to estimate leverage scores. And just from this alone, you see that it's only going to do well if the underlying matrix is well conditioned. So there's going to be a condition number that appears in the estimate that is an artifact of this algorithm, which isn't really the right algorithm that you want to do. So then we considered the two-phase sampling algorithm, which is just the same as before, except now we draw uniform samples from the matrix, and then we construct estimates of the leverage scores just by looking at the squared L2 norms of the rows and the columns of the resulting zero-filled sample matrix, properly normalized. Okay, so we're using these as our estimates for the leverage scores. And then from those estimates, we construct a weighted sampling distribution and then draw a second batch of samples according to that weighted distribution. So we can prove some things about this algorithm. So we're going to look at just write the leverage scores, the left and right leverage scores, in decreasing rearrangement. That's why I put the parentheses around 1, 2, and n. So assume they're in decreasing rearrangement. We can say that if the phase 1 sampling probability, so the probability that you sample an entry in the first phase, where we do uniform sampling, is greater than this number, which has a dependence on the condition number kappa, times the minimum of this quantity over a parameter t from 1 to n, then with nice probability, the estimated leverage scores will be bounded above and below by the underlying true leverage scores, at least the largest t of them. Okay, so if t equals 1, then we essentially just recover the standard sample complexity from uniform sampling matrix completion. But if t is a little bit larger than 1, you can see that we get a gain because the leverage scores are numbers that are less than 1. So the square of a number that's less than 1 is smaller than the number. So what this says is, well, if there are only a small number of the leverage scores, row and column leverage scores, that are bigger than the rest of them, then we can estimate those few big ones and gain a factor, and the sample complexity of that will be smaller than the sample complexity of matrix completion because those big numbers get squared here. So they get squashed down, and only the t plus first largest leverage score comes into play without a square in the sample complexity. So this looks a little bit crazy. So let's look at some what this implies for the two-phase matrix completion algorithm. What it implies for the algorithm is that if we use this number of samples for the phase 1 sampling, and then if we can get those estimates of leverage scores, we only need on the order of n times r times log squared n samples for phase 2, the weighted sampling. Then together, those samples will be sufficient to recover a rank R matrix M with a good probability. So you see here the bottleneck is in the phase 1 sampling, and some special cases are, okay, uniformly flat leverage scores. This means that all the leverage scores are on the order R over n. So up to the dependence on the condition number, our sampling complexity matches just the standard n times r log squared n result. So it recovers that result as a special case. There are some other cases we could look at. If the largest t leverage scores, left and right leverage scores, are on the order of square root r over n, I think of this as a medium coherence range. And the remaining leverage scores are uniformly small, r over n. Then this adaptive sampling, we still only need on the order of n times r times log squared n samples, multiplied by the t, the number of larger leverage scores. So in this medium coherence range, we can get a sample complexity from adaptive sampling that's much smaller than what you would get by just doing uniform sampling. And then more generally, we can look at matrices whose leverage scores have a power law type distribution. Just one particular example is if the largest so many leverage scores are decaying at a rate of like I did a 3/2, but this could be any rate greater than 1. Then this sample complexity is on the order of n to the 4/3, whereas the sample complexity you get from uniform sampling is on the order of n to the 3/2. So the sample complexity is reduced. And I have some simulations. So these are just pictures of the 4 different power law type matrices that I'm going to look at experiments for. So I don't know if you can even see, but this matrix over here is very, very coherent. Almost all of its energy is just over here. So it has very, very fast power law decay. And then we have a matrix that's a little more diffuse, a matrix that is almost incoherent, but still has some biased leverage scores, and then a sort of classical incoherent matrix. And if you can see here, I'm plotting the probability of exact recovery and plotting sort of the phase transitions for uniform sampling versus the two-phase sampling. And if you can't see, the results are just what you would expect, that as we get more and more coherent, the two-phase sampling diverges from the uniform sampling and can do much, much better, or complete matrices using fewer samples. And then this is just the average sampling probability over here. So here, the condition number is 1 in all of these, but we tried, again, with the same types of matrices, except now condition number 100, and surprisingly found that the results were the same as when the condition number was 1. So even when the condition number is 100, the two-phase sampling results in the ability to complete a low-rank matrix from many fewer samples than uniform sampling. And the plots almost looked unchanged. So this suggests that even this algorithm that we're using doesn't depend on the condition number of the underlying matrix that much. And then we considered different types of low-rank matrices. So here's just a block diagonal matrix. So it's rank 5. And I don't know if you can see this, but this is rank 4, and it's a block diagonal matrix where the blocks are very different sizes. So this is incoherent, and this is more coherent. And you see that for the completely incoherent matrix, uniform sampling does a little better, because uniform sampling is the optimal sampling probability when you're incoherent. So two-phase does slightly worse. But for the coherent block diagonal matrix, two-phase sampling does better than uniform sampling. Then we increased the condition number and looked still. So increasing the condition number here corresponds to changing the values of the blocks to making the values more dynamic. And here, the two-phase matrix completion did worse than the uniform matrix completion, even though when we look at the sort of reconstruction error, they look about the same. But uniform matrix completion can complete exactly from fewer samples. So this is a case where we do worse. So I'm showing you good results and results where we do worse. But I do want to emphasize that the two-phase type of adaptive sampling fundamentally cannot do that much worse than uniform sampling, because just from the first batch of uniform samples, especially if you use most of your budget for the uniform samples, you'll do at least as well as the matrix completion theory from those uniform samples. You're just adding an additional batch of samples drawn from a weighted distribution, and if your guess on that weighted distribution is bad, then you'll do about as well as uniform sampling with the uniform samples. If it's good, then you have the ability to do much better than if you took all your samples uniformly. So again, just to review, we have sort of the classical matrix completion result says that any rank R matrix can be completed from a number of uniform samples, n squared times the maximum leverage score. And this is good when all the leverage scores are uniformly flat. More generally, if we knew what the leverage scores were in advance, then we can come up with a weighted sampling strategy that requires only on the order of n times r samples to complete the matrix, but this requires that we have this prior knowledge, which is unrealistic. So we looked at a two-phase sampling procedure, which first samples entries uniformly and then estimates the leverage scores from those samples and then draws samples from a different distribution, and showed basically sample complexity for this algorithm, which always at least matches the sample complexity from uniform sampling up to a constant and condition number, but can also lead to sample complexity that's much, much lower. Whether it's optimally low, I don't know. I don't know what lower bounds are for these types of results, but future directions are definitely to improve the dependence on the condition number The experiment suggests that there's very mild dependence of the two-phase sampling on the condition number. Theory for noisy and or nearly low-rank matrices of the same type that we have for the standard matrix completion. And maybe more broadly, extensions to other types of flavors of these algorithms, reduced sample complexity if we have some sparsity and incoherence in measurements, any of these types of problems, to see if adaptive sampling can reduce the sample complexity in any of those settings as well. 30 minutes.
Questions?
So you talked about two-phase sampling. Is there any reason why not to do, let's say, log n phases and you pay another extra log n factor in the total number of entries that you will do?
Experimentally, we didn't see any gains from using more than two phases. So I think that there could be a gain if you do something more clever in the different phases than just uniform weighted, updated. There's probably some way to do a more clever combination or alternation than what we tested for.
Questions? Okay, let's thank Rachel again.